In this video, we will learn session 8.5 Applications to Physics. Many problems in physics are solved by calculating integrals. We'll start this session by introducing the concept of work. If a constant force F is applied to move an object a distance d, we define the work W done to be the product W is F times D. So work done is equal to force times distance. So next we'll talk about the units. And there are several sets of units in common use. To measure work, we will generally use the two sets of units, international, also called SI, and British units. So let's first look at the international units. Also called SI units. In the international units, the unit of force is Newton. NT is short for Newton. The unit of distance is meter. M is short for meter. The unit of work is the joule. J is short for joule. In British units, the unit of force is the pound. LB is short for pound. The unit of distance is foot. FT is short for foot. The unit of work is foot, pound. FT/LB is short for foot pound. This is two common use units sets. As we look at an example. Calculate the work done on an object when a force of 2 newtons moves at 12 meters. B. A 3-pound force move at 4 feet. So we first look at question A. A force of 2 newtons moves at 12 meters. So this is used in the international units. So by the formula of the work, so work done is equal to the force times distance. So it's 2 newtons times 12 meters. This is 24 joule. Question B. A 3-pound force, 3 pound, move it 4 feet. So pound feet. So this is using the British units. So the unit of the work should be foot-pound. So work done by the formula is equal to 3 pound times 4 feet. So this is 12 feet pound. So this is the first example. The second example, we look at a case when the force is not a constant. Instead, it's a function of the variable x. Example 2, Hooke's law says that the force F required to compress the spring by a distance x in meters from its equilibrium position is given by F is key x for some constant k. Find the work done in compressing the spring by 0.1 meters if K is 8 newtons meter. Sorry, this is meter. So let's draw a picture to illustrate this example. So this is the wall, and we have a spring. And suppose the equilibrium position is here. Equilibrium position. So the spring is compressed by a distance of x. This is x. Now since this K is in newtons meter and x in meters, and we know that F is kx. So we have F is 8x newtons. F is 8x newtons. Since the force varies with x, and the force varies with x, we divide the distance moved into small increments delta x. So we suppose this is delta x. Delta x. So work done in moving through an increment delta x is the force times distance. So work down in moving through an increment, delta x is approximately equal f delta x, force times distance. So this is 8x delta x joules. So summing over all increments gives the Riemann sum approximation. So the total work is approximately equal to the sum of all increments. Then taking the limit as delta x goes to 0 gives total work done is from 0 to 0.1 8x dx. So because we express the spring by 0.1 meters, so x is from 0 to 0.1. So this is 4x squared 0 to 0.1. So this is 4 times 0.1 squared minus 0. So this is 0.04 joules. This is example 2. So in general, if force is a function of position x, we have the following formula for calculating the work done. If force is a function of x or position x, then in moving from axis A to axis B is given by work done is equal to the integral of fx from A to B. This is the formula. So next we talk about the V. So V is the force. V is the force exerted on an object due to the Earth's gravity acting on its mass. In international units or SI units, the V of an object of mass m kilogram is mg newtons, where g is 9.8 meter per s square. Is g is the acceleration due to gravity at the Earth's surface. in British units. This is in international units. In British units, the pound is a unit of force. This is not of mass. The pound is a unit of force. So when we see an object is 10 pounds, we mean that the V is 10 pounds. That is the Earth's gravitational field exerts 10 pounds of force on it. So next we look at an example. How much work is done in lifting a 5-pound book 3 feet off the floor? B. 1.5 kilogram book 2 meters off the floor. So we first look at question A. How much work is done in lifting a 5-pound book 3 feet off the floor? So the force due to gravity is 5 pounds. 5 pounds is the force. So we have the work done is equal to F, the force times distance. So it's 5 pounds times 3 feet. This is 15 foot-pounds. This is A. Part B. A 1.5 kilogram book 2 meters off the floor. 1.5 kilogram is the mass. So we first find the force. The force due to gravity is mg. So F is mg. So this is 1.5 kilogram times g is 9.8 meter second square. So work is Fd. This is 1.5 kilogram times 9.8 meter second square times 2 meters. Distance is 2 meters. So this is 29.4 joules. Then we finished this example.